I'm going to talk today about how we can understand in reality what's occupying the radio spectrum, what the characteristics of different pieces of the spectrum are. If you look at the radio regulations or national charts of spectrum allocation, everything looks quite well defined and tidy. You've got different services allocated in different bands, and you've got hard edges between the bands. We have primary services and secondary services. So in principle, we know exactly what's going on in all these colourful chunks of spectrum. But of course, the tidy world of the regulator may not correspond to what's actually going on in the real world. And so it can be important to sometimes take a reality check and to see what's really happening. And you may need to do this for various reasons. So you may want to check what the actual occupancy of the spectrum is, as opposed to what's going on in your frequency allocation charts. This may be to check for illicit use, or to check that licensees are actually adhering to the frequencies or perhaps the powers they've been licensed. You may want to know something about the congestion in the radio spectrum. Is it filling up too rapidly? Are there blocks of unused spectrum that could be redeployed for other purposes? You may receive interference complaints. There may be problems with service quality, and you may need to investigate what's causing a fall off in consumers' perceived quality of service. And at a fairly basic level, if you're rolling out a new service of whatever sort, whether it's a cellular mobile service, or whether it's broadcasting, or even a mobile satellite service, you may need to be able to estimate the coverage, either to check that a service that's already deployed is operating as expected, or to plan where new services are needed. You may need to find the holes in coverage of an existing network. And at the most fundamental level, if you're going to be rolling out any services that use the radio spectrum, you need to understand what the environment looks like. And most fundamentally, that's limited by noise levels, which could be due to natural noise or due to man-made noise. And you also need to understand a bit about the propagation of radio waves at different ranges and at different times and different frequencies. So there are many reasons we need to understand the characteristics of the spectrum, and these are just a few of them. I'm just going to give a very quick non-technical gallop through some of the issues that are thrown up. So thinking about spectrum occupancy, as I say, we may need to know whether there are licensed services using the spectrum, whether people are sticking to their license conditions, whether there's unused spectrum lying around that may be used for other things, and where congestion might be a problem. And these sorts of measurements don't necessarily require highly calibrated, very technical measurements to be made. Perhaps we can take a fairly high level view and answer these questions using fairly straightforward equipment, but we probably will need to look over a wide spatial area. We may need to cover quite a bit of geography. Probably measurement from a single fixed point isn't going to be adequate to understand what's going on, because the great variability in signal strength with geography. And historically, many spectrum regulators have used fixed monitoring networks, and these can allow, if you deploy fixed monitoring nodes in cities, this sort of network can be very useful for identifying FM radio pirate stations. This has been one of the major uses of such fixed monitoring in the past. Or you may use it to understand the congestion on things like business radio channels, private mobile radio channels in the VHF and UHF range. So you may need to revise your licensing procedures if those channels are being overused. And fixed nodes like this can help you build up a robust picture of how spectrum occupancy is changing over time. You may be interested in the sort of daily peaks and troughs of traffic, understanding when the busy hour falls, and those sorts of constraints, or you may be interested in longer term trends in spectrum use on a timescale of years. And if you've got a series of fixed nodes, monitoring nodes, and you're carrying out the same monitoring with the same equipment over many years, this can build up a pretty valuable picture. But in other ways, this sort of network is very limited. It doesn't give you much insight into the geographical distribution of interference and spectrum use. And if you're trying to use it to understand interference problems, or perhaps where illicit frequency use is happening, this can be quite difficult, even with direction finding implemented at these sorts of sites. Given the relatively short propagation ranges involved at VHF, UHF and above, most realistic fixed monitoring networks are going to struggle to be able to produce a very robust understanding of what's going on in the spectrum with administration. And you also have a problem that the equipment configuration may be fairly inflexible. You'll likely have a few antennas on a mast of particular fixed gain, frequency coverage. And if you're using the same equipment to make the same measurements over a long period of time, which is in some ways very useful, it can mean that the equipment may not evolve to accommodate new services that are appearing in the bands, in terms of either the instantaneous channel bandwidth that you can measure, or the things that you can demodulate. And this is where it becomes very useful to be able to deploy mobile or portable equipment that you can configure as necessary. The picture there is the interior of the Plum monitoring vehicle, a Land Rover with various pump-up masts, and we can fit this to look at any part of the spectrum from MF and LF through the sort of shortwave spectrum right up to millimeter waves up at 28 gigahertz or beyond for very specific purposes. So this gives you great flexibility. You can travel to where there may be reports of interference, or you may want to investigate the performance of a particular news service. But it implies that you've got to have staff that can adapt equipment to specific needs. And it also suffers from the great disadvantage that it doesn't build this sort of understanding of spectrum use over time, over a long period. So I think the message is that there's no one size fits all type solution for spectrum monitoring, that you need a variety of things in your toolkit. An example of wide area broadband measurements, just to understand spectrum occupancy, is some work we did in Ethiopia with our associates at Sitcog, a local consultancy company who provided great value. We were starting from a background of wanting to understand what was actually deployed there in a situation in which the records may not have been completely comprehensive. So we wanted to see how the expected distribution of spectrum use matched up with that in the notional allocation table. So this sort of work doesn't require very precisely calibrated equipment, and we were able to make flexible use of hired cars with portable equipment, magnetically mounted antennas on the car roof, and we could drive around and log a wide chunk of the spectrum simultaneously while following routes around the country. And the plot here on the left is of the spectrum running from about 100 megahertz up to 4 gigahertz, so enough to embrace most of the common uses of spectrum. And you can see here plots of these are plots against time. So time is on the vertical axis, frequency on the horizontal axis. And you can see on the left there are a number of broadcast services, UHF television, FM radio, and then the expected cellular frequency bands showing a high degree of occupancy, even as the car travelled over many kilometres. You can see also there's a tendency for signal strength to get lower as you move up in frequency. This is unsurprising because the antennas obviously become less and less efficient in terms of capturing signal strength. So there comes a point probably around about 4 gigahertz where it gets very hard to make meaningful mobile surveys of this kind, just because to detect signals over a useful range requires highly directional and higher gain antennas to dig down into the noise to understand what sort of signals are out there. There are also other issues with this sort of monitoring. It's careful not to take things at face value and just to use equipment on the default settings. The plot on the right here shows examples of some spurious signals that were seen in the higher spectrum indicated by the arrows. And you might think that there's a lot of illicit spectrum use going on at 2 or 3 gigahertz. That's not the case. The signals you see here are just artifacts produced by the spectrum analyzer when it encounters very strong signals at lower frequencies. And this generates these spurious signals. So the answer to this is that in those situations, you should put more attenuation. You should lower the sensitivity of the equipment to stop the overload. And it's possible that various pieces of equipment will do this automatically, but it does. The slide here is really just to indicate that you need to interpret measurements very carefully, and you need technically literate people to interpret these measurements very often. Moving on to more precise technical understanding of coverage and the signals in space. We do quite a lot of broadcast system coverage definitions. So here we're not just concerned with knowing what signals are occupying spectrum, but we want to characterize those signals very carefully to understand where the limits of coverage might lie. And to do this, you need to make use of carefully calibrated antenna systems like the one shown on the left. This was some measurements we did in the UK, looking at the extent of DAB, digital audio broadcast coverage at around 200 megahertz. And it's notoriously difficult to understand the gain of antennas fitted to cars without very careful measurements, and the car body can affect the response of the antenna very substantially. So we've mounted this antenna on a well-defined metal surface here, so that we have a very repeatable antenna pattern that allows us to estimate the signal strength very precisely. That's not always possible. On the right here, you see some measurements we did in the Falkland Islands in the South Atlantic. And here we didn't have we were just provided with a car, and we had to transport antennas on a plane. And so we weren't able to take this large sheet of metal with us. So these antennas would have a much higher uncertainty as to what the actual gain and the pattern of the antennas look like. So the measurements we made in the Falkland Islands will come with a significantly higher degree of uncertainty than the measurements we made in the UK. So this sort of thing needs to be allowed for in interpreting coverage measurements. Broadcast services are relatively straightforward because you're looking at a constant and well-defined transmitted signal. Validation of cellular systems is much harder. There is obviously a broadcast channel in all cellular systems designed for handsets entering a coverage area to be able to find and establish communication through the base station. So in systems of 2, 3, 4G, it's been relatively straightforward to grab hold of that broadcast channel and make measurements on it. What that doesn't do, of course, is tell you much about the traffic that a particular cell can handle at a particular time, and that'll depend obviously on the behavior of other users and the degree of loading of a cell. But there's also a more fundamental problem as we move from 4G to 5G, in that the idea of a cell-based network is disappearing to be replaced by one that's based around the individual beams that are synthesized from particular base stations on an ad hoc basis. So you have beams that can sweep across the coverage area of a particular base station, and you no longer have a fixed signal power emanating from the base station. So with 5G systems, you need to do a much more complicated search for the beams of the base stations as they scan, looking for new users, and to process that very rapidly time-changing behavior. And a lot of measurements made of cellular networks are passive, but as I say, you also need to understand the impact of cell loading. And in high traffic areas, it's very often the case that operators may be wanting to deploy and densify networks with additional nodes. And this really calls for an understanding of the constraints due to other users of the network. And to get a handle on that sort of issue, you really need to be doing active probing of the network. And this is the sort of work that is very much offered as a service by a relatively small number of well-established providers and companies offering to do this sort of survey work on a regular basis for operators. And the sort of tools they use, you can see a backpack here, which can contain up to 6 commercial handsets that are then driven by a monitoring unit, in this case a Keysight product, to actively probe and investigate the traffic that can be handled by a particular cellular network. So we talked a bit about sensing the signals that are intentionally being broadcast, but any radio signal is fundamentally limited by the noise in the environment. Even when you've got no interference, the quality of a radio service will be determined by noise, which could be natural noise from the atmosphere, or even from celestial sources, from galaxies and from the sun. And the plot here shows different noise sources across the radio spectrum, running from very low frequencies, 10 kilohertz at the bottom here, up through the AM radio wave bands, and up to FM radio at this end of the spectrum. And you can see that the general tendency is for noise to decrease as you move higher in frequency. Below the VHF range, noise is dominated by atmospheric noise, and this is really effectively lightning storms and the noise, the electrical noise generated by lightning, propagating around the world, being bounced off the ionosphere. And that falls away pretty rapidly above about 30 megahertz or so as you move into the VHF area. And it's replaced by noise from the galaxy, from the sun, and from celestial sources, which at lower frequencies is attenuated by the atmosphere, but that starts to become dominant as you move into higher frequencies. But probably the most significant effect of all is that of man-made noise, which is highlighted on this curve here. And for most of the frequencies we're concerned with, man-made noise will be the dominant noise source. If we look at the next graph, these graphs, by the way, are taken from an ITUR recommendation, P372, which goes into a lot of detail about understanding and measuring and allowing for radio noise. Again, we've got, this is looking at higher frequencies from around the VHF radio band at 100 megahertz up to 100 gigahertz. And you can see that if you point an antenna at these frequencies at the sun, that tends to dominate. The sun is sometimes used as a reference source for antenna calibration because it's a very strong source, but it's very seldom you'll be deliberately pointing a high gain antenna at the sun. So once again, you can see that man-made noise tends to dominate the power that's out there in the absence of interference. But unfortunately, this graph peters out just below about a gigahertz. And there's currently a great deal of work being done to understand the limits imposed by man-made noise on radio services. There's some information in this ITU recommendation specifically about man-made noise levels outdoors, and they've attempted to define the sort of median noise levels that are expected in different environments. So we move from city to residential to rural, and then a quiet rural area far away from any sources of electromagnetic interference. And here again, you see this dotted line which shows the galactic noise levels from the sun and from galactic sources. And you can see that these are generally 10, 20, 30 dBs below the man-made noise level. So man-made electrical noise is the thing that will determine service quality in many cases, probably most cases, and we need to understand it. It's very hard to get a firm grip on this because it changes so dramatically over such a small area. And it's a growing problem indoors where there really isn't much information. The ITU acknowledged that there's insufficient measurement data to understand the levels of man-made noise indoors. But this is a problem that's exercised a lot of regulators, including Ofcom, who've sponsored quite a bit of work in this area. Now, if you look at this is a spectrum analyzer plot showing that the VHF spectrum in a noise-free environment, but if you then move into a typical domestic environment with a few halogen lights and some power supplies and typical items for electrical equipment, this is the sort of difference you see in the spectrum. And you can see that you're jumping up at maybe 40 dBs, so several 100,000 times increase in noise levels due to interference from these typical domestic devices. And that has a massive effect on the usability of radio services. So these were some measurements we did comparing noise levels at the frequencies used by DAB services around 200 megahertz and those used by cellular radio services around 800 megahertz. And you can see in line with those ITU charts that the interference at 200 megahertz is dramatically stronger in a typical suburban house than the interference at higher frequencies. And this is replicated in many domains, and it's one of the drivers that has led users of radio services over the years to migrate to higher and higher frequencies. Obviously, another driver is the much larger bandwidths available, but the freedom from man-made noise is also a useful benefit of moving to higher frequencies. So one of the problems of understanding the impact of noise is that it varies so rapidly over a very small area. And the same is true with understanding issues of spectrum congestion in particularly the ISM bands, the bands used by Wi-Fi, Bluetooth, and similar services, where you have a relatively small number of hotspots, where you have dense spectrum use and possibly a lot of mutual interference between the different services occupying these bands. But then if you move 100 meters, or half a kilometre away, you have an entirely different pattern of use. So to try to build a statistical pattern of spectrum use and congestion by these services can be really very problematic. We've been doing a bit of sampling in hotspot locations of the use and congestion of these bands, particularly the ISM band at 2.4 gigahertz. And this is quite a laborious exercise, though it can be done as a background activity while doing other things. And we've been taking the portable spectrum analyzer you see here to a variety of public locations, railway terminals, airports, libraries, this sort of thing. And these are measurements being done in a university library, and you can leave the spectrum analyzer running for maybe half an hour to build up a picture of spectrum use. And you very quickly fingerprint different users of the spectrum. The graph on the right here is displaying the statistics of spectrum use. So the blue line at the bottom shows the power that you see for 50% of the time at each of these frequencies. And then the other curves show the power that exists for smaller and smaller percentages of time. So you can see that for 50% of the time, most of the signals received are at around this minus 100 dBm mark. But if you look at 1% time, the signals are 30 dBs or so higher. So you have to allow for that variability in planning or understanding what sort of coverage you might get. And there are various fingerprints you can see in the spectrum here. You can see there's probably a CCTV camera operating on this particular frequency. You can pick out the different Wi-Fi access points that are using 3 overlapping channels that you have in this band, plus another channel. And then you can see evidence of Bluetooth, the so-called advertising channels that Bluetooth devices use to find each other. So you can see there are quite a lot of Bluetooth devices out there. And gathering this sort of data allows you to understand the quality of service you could deliver using this band, either to Wi-Fi devices or maybe Bluetooth audio streaming. So it's very hard to understand the spatial variability of signals, but it's also takes a lot of work to understand the temporal variability. And looking at signals on a much greater scale, the changes in the atmospheric refractivity with the weather can mean that signals that normally only have a range of a few kilometers may travel very much further, may travel beyond the horizon. This is a sketch of signals leaving a transmitter and being captured in the sort of atmospheric duct that you get, typically during high pressure summer weather conditions. And this can cause signals, particularly from high power broadcast transmitters or maybe telemetry transmitters or PMR transmitters operating in the UHF spectrum or microwave fixed links. They can propagate over maybe 1,000 kilometers rather than their design range of a few tens of kilometers due to these changes in the atmosphere. And these sorts of effects only really are significant for a small percentage of time. So to understand them, you need to do some long-term logging. We carried out an exercise for Ofcom a few years ago now on the east coast of England, monitoring signals from the Netherlands. And for a period of a year or so, we looked at the changes in signal strength, and they're pretty dramatic. The plot here shows the way in which signal levels changed during the month of August. And in particular, there's a weather map on the right here showing that there's a high pressure area extending from the Netherlands across the North Sea to the south of England. And while that weather front, or while that high pressure zone existed, you can see that the signal levels increased from their normal value of around 25 dB microvolts per meter up to a dramatically higher level, some 50 dBs or so higher. And the implication of this is that any service using this portion of the spectrum, this is in the UHF TV band, it's going to be very hard to design a service that can accommodate these dramatic changes in the interference environment. But another problem is that there really isn't much data. Looks very likely that climate change is affecting the statistics of these sorts of long-range interference events. But because it requires a commitment to long-term measurements to understand these statistics, and because it's not very academically exciting, you've probably got few universities interested in doing these sorts of measurements, and because there's no immediate commercial benefit to making these measurements, there's not really much being done in industry. So it's in danger of becoming a subject that falls between the cracks. So I've talked a bit about the problems of making measurements over wide areas and sampling signals that can change very quickly spatially, and the need for long-term measurements to understand temporal variations. And it all seems very hard, but technology is helping because receiving equipment is getting much cheaper and more flexible. There are a lot of commercial off-the-shelf devices, software-defined radios that can be configured very cheaply and considered almost disposable and left operating in scattered locations, or they could be installed in cars that are roaming the country anyway, maybe as utility vehicles or salespeople's car fleets, and they can be carrying out autonomous monitoring with very little manual intervention and at very low cost. There's a selection of devices on the right here. There are a couple of consumer devices that cost just a couple of hundred UK pounds, and some slightly more professional devices that cost a few £1,000s. And these can be configured to something like a Raspberry Pi computer and left running autonomously or connected to the internet to feed data back remotely. So this sort of technique potentially allows you to do a lot of spectrum monitoring on the cheap, so long as I said in an earlier slide, you have the resources to understand and interpret the data correctly, and that you avoid being misled by some of the limitations of this relatively cheap equipment, which can lead to problems with overloading and other effects that have to be guarded against. The device here on the left was developed by the BBC. They were interested to understand the statistics of interference to domestic TV reception, and they made a large number of these little items which contain a small receiver that can be connected to a standard TV antenna without affecting the signal at the TV receiver, and just report back over the internet what the signal quality is. And these have been deployed in about 50 locations around the country, just to keep a constant eye on the quality of signal being received. And there are other new approaches that can be used. Drones are something we've been looking at as a way of sampling a large area in a small amount of time. And there are problems with ensuring that you've got a reliable antenna gain so that you really know what you're sampling. It can be quite hard to make a good antenna that will provide reliable results when attached to a drone. But more of a problem we've found in trying to use these sorts of systems has been that safety regulations quite reasonably exclude you from using drones in many of the areas that you'd want to be making measurements in cities and built up areas. And another option is to use the crowdsourced data that's increasingly available from commercial providers and others. And here you're trading technical quality and reliability of results for the sheer quantity of data that's available. And this can be an extremely valuable source of data, particularly for cellular coverage, but it needs to be used with great care and not to be taken at face value. So you really need to talk to the provider of crowdsourced data about exactly how the data was derived and processed. So I think if there's one takeaway point from this brief talk, it is that there's no one simple solution. There's no magic bullet for understanding what's going on out there in the radio spectrum. You need a toolkit approach of adapting existing tools for specific purposes, and you need a good understanding of the possibilities, but also the limitations of all the equipment that's becoming available. So I'll end there and take any questions you may have.
Thank you very much, Richard. So I received 3 questions for you. The first one is, you talked about how the mobile monitoring can reach up to 4 gigahertz. Is there an effective way of measuring use of spectrum above this?
Yes, it's going to be harder to do from the sort of mobile monitoring equipment that I was looking at there, where you were just mounting equipment on a hire car. If you've got an installation such as the one we have on our Land Rover, where you can configure it to use high gain antennas, and you can stop and make measurements at fixed locations, maybe briefly, but you need to stop the vehicle and then use the antenna, the high gain antenna. You can scan all azimuths, so you can look around the vehicle with a high gain antenna and see what signals emerge from the noise as you move the antenna around. That's one option. And mobile measurements are potentially possible with if you have access to some very expensive hardware that can use active antenna systems to synthesize high gain antenna beams while you're traveling. So these are the sort of systems that are really being developed for things like satellite Earth stations in motion, if you're trying to provide services from geostationary or non-geostationary satellites to vehicles. There are a lot of people working on high gain antennas that can scan in real time as the vehicle moves. And you could use these sorts of systems for real-time spectrum monitoring at much higher frequencies from moving vehicles, but it's not something I've seen done yet. So I think at the higher frequencies above 4 gigahertz, you're really looking at a sort of transportable setup with a larger vehicle with a rotatable antenna of high gain tailored to a particular frequency on the roof of the vehicle.
Okay, thanks. The second question is there a limitation to using movement to higher frequencies as a solution to man-made noises?
Probably not is the simple answer. I guess by movement you're thinking of moving away from the source of the noise, but the problem is that particularly indoors, the very areas where you've got a lot of electrical noise are the very areas where people are trying to consume these services. So it's just a fundamental incompatibility really between the very high levels of electrical noise that you see and the desire to operate wireless services in those environments. And this is really something that can only be solved with stricter regulation of EMC, electromagnetic compatibility and type approval. And there's a lot of equipment coming onto the market where it clearly doesn't meet EMC standards, but this is a regulatory issue.
Yeah. Okay. Another question is, when you showed the indoor interference, you talked about issues up to 100 megahertz. Are there any similar issues at higher frequencies like the C-band?
Yeah, that's a very good question. The apologies for the dog in the background. And this is something that the ITU in particular and national regulators are trying to address. You can see that the graph here, these are all suspiciously straight line graphs which suggests that they're not based on an enormous amount of data because they're tremendously simple. And they show that the expected interference falls off quite quickly with as you move up in frequency. But anecdotally, I've certainly seen an increase in interference at higher and higher frequencies. So it used to be very seldom that you'd have much man-made noise beyond about 100 megahertz. And now that's crept up into the UHF spectrum. I think C-band is probably still quite a quiet environment, but I think it's something that regulators and users of the radio spectrum need to pay attention to, as particularly things like computer clock speeds become faster and faster. The harmonics generated by those will tend to pollute higher and higher frequencies. So something that needs to be watched.
Okay. Does the monitoring equipment itself sometimes cause interference in certain bands?
It does. It's something we've had issues with, and it can be extremely embarrassing to be seeing a lot of interference and be hunting everywhere for the cause of the interference, only to discover that it is in fact the laptop computer that you're using to drive your logging equipment that's causing the interference. So that, yes, that is something to be very aware of, and it comes back to the fact that you've got a lot of equipment that can be very flexibly configured and quite cheaply configured these days, but it needs to be used with great caution. And I think one of the problems I've found is that there seems to be an industry shortage of RF engineers with the capability to interpret what they're seeing from some of these measurements, and there's a danger things can be taken at face value when perhaps they should not be. So yeah, definitely one to watch.
Okay, a last question is if you can speak a little bit about temporal interference and the effect of climate change and high pressure environments in certain bands, and what sorts of challenges it presents in terms of what works for measurement currently and usage.
Yeah, this is something, again, I've only really got anecdotal information to work on, because a lot of these measurements of variability of signals were made 30, 40, 50 years ago, when people were starting to use these frequencies for the first time over wide areas. And there hasn't been much done recently, and certainly no reliable tracking over time. So what you can say is that we understand very well the relationship between these sorts of enormous signal variation and weather patterns. And so luckily we've got a good understanding of the changes in weather patterns. So these could be used to run the models that relate the patterns we see in the weather to the changes in signal strength. So we have the ability, certainly, to understand how the statistics are changing and how the models provided by people like the ITU might need to be modified. Obviously, we're seeing more and more extreme weather events. It's possible that with the extra energy in the atmosphere, with climate change and global warming, that we'll see less of the long period, well-established high pressure zones that we've typically seen around the UK in the summer, that they may be subject to more rapid change, which may preclude some of the these long instances of ducting and anomalous propagation we've seen in the past. But we don't really know. I think it's an active area that should be investigated. But okay. The tools are certainly there. The data is there, even if we haven't got the direct measurements of of radio signals, I think we can use historical and current meteorological data to infer what the effects would be. Okay, thank you, Richard. I think we are coming to the end of this webinar. Thank you very much. It was very interesting, very useful. We will send the presentation materials to the people who requested it, and there will be a record of this presentation that will be put on our website, on Plum's website. So thank you very much, and have a good day, and see you next time for the next webinar. Thank you. Bye. Thank you, everyone.